Sapugay, a second-year BSIT student from Davao del Norte State College. And I am going to visualize one of the algorithm, which is the Bellman-ford shortest path algorithm. And I hope you will like it. The Bellman-ford algorithm is an algorithm that computes shortest paths from a single source vertex to all of the other vertices in a weighted directed graph. Consider the example graph. This is a vertex. This represents the directed edge. This represents the weight of the edge. As we can see, we have 4 vertices, and S is our source vertex. Notations we will use are given below. U means start vertex. V means the end vertex. U to V means the directed edge from vertex U to V. WUV means the weight of the directed edge from U to V. If there are n vertices, then we will iterate n minus 1 to get the shortest distance. We have 4 vertices, so 4 minus 1 is equal to 3. We have 3 iterations to perform, but we need to perform the 4th iteration to check if there is a negative cycle. And this table is the example of our edge and weight. We have 2 arrays, the D and the P. D contains the distance. P contains the predecessor of the respective vertices, and this column represents the vertex name. These cells will hold the distance to the respective vertex from source vertex S. These cells will hold the predecessor of the respective vertex. We will start to fill the distance array D. As S is the source vertex, so we fill it with value 0. And the rest with infinity. And fill the predecessor with a line. This is how we relax an edge. Relax UV, V that D is greater than U that D, then plus the weight UV. V that P is now equal to U. We need to relax an edge so we can find the shorter path to reach V. We will perform now the iteration 1. Consider the following 2 arrays with a value of 0 and infinity, and the predecessor is empty. Proceed to the first edge. Relax SA. As infinity is greater than 0 plus 4? Yes. And then update. Vertex A in distance has now the value of 4 and the predecessor of S. Proceed to the next edge. Relax SB. Infinity is greater than 0 plus 1? Yes. And then update. Vertex B in distance has now the value of 1 with the predecessor of S. Proceed to our third edge. Relax AS. If 0 is greater than 4 plus 2, no. 4 plus 2 is equal to 6. 6 is greater than 4, so we will not update. Then move to our next edge. Proceed to our fourth edge. Relax AC. Is infinity is greater than 4 plus 3? Yes. And then update. Vertex C and distance has now the value of 7 because 4 plus 3 is equal to 7 with the predecessor of A. Proceed to our fifth edge. Relax BC. Is 7 is greater than 1 plus 5? Yes. And then update. Vertex C and distance has now the value of 6 with the predecessor of B. Proceed to our last edge. Relax CS. Is 0 is greater than 6 plus negative 2? No. 6 plus negative 2 is equal to 4, and 4 is greater than 0, so we will not update. We're done with our first iteration. We're now in our second iteration. Proceed to our first edge in iteration 2. Relax SA. Is 4 is greater than 0 plus 4? No. 0 plus 4 is equal to 4, and 4 is just equal to 4, so we will not update. Proceed to our second edge. Relax SP. Is 1 is greater than 0 plus 1? No. We will not update because it is still equal. We're now in our third edge. Relax AS. Is 0 is greater than 4 plus 2? No. 4 plus 2 is equal to 6. And 6 is greater than 0, so we will not update. We're now in our fourth edge. Relax AC. Is 6 is greater than 4 plus 3? No. 4 plus 3 is equal to 7. And 7 is greater than 6. So, we will not update. Proceed in our fifth edge. Relax BC. Is 6 is greater than 1 plus 5? No. And we will not update because it is still equal. We're now in our last edge. Relax CS. Is 0 is greater than 6 plus negative 2? No. 6 plus negative 2 is equal to 4. And 4 is greater than 0. So we will not update. We're done with our iteration 2. We're now in iteration 3. Iteration 3 is still the same in iteration 2, but I will still show you the result. In order to check if there is no negative cycle, we have to perform the fourth iteration. I try it and still no changes in distance, so the graph has no negative cycle. We will now graph the result. We will start in vertex A. Vertex A has a predecessor of S. So mark as S2A with a weight of 4. Vertex B has the predecessor of S. So mark as S2B with a weight of 1. We will now graph the last vertex, which is C. C has the predecessor of B. So mark as C2B with a weight of 6. And this is now our final graph.